have an electric field going off to the right. I have my dipole moment in it, rotating about some point. Misuse the word again. I have a dipole, electric dipole in it, and it's going to rotate about its center. I have a force acting this way. It's an electric force acting on that, an electric force acting back this way. Just a cleaner version of what we have done. I'm going to assume some angle here, theta. We'll call it theta sub I, cleverly, for initial. And it is going to rotate through some mechanism to some final angle. Now, if I just stuck a dipole in that electric field, it's not going to do that. If I just put it right there and took my hands off, the thing's going to rotate the other direction. But if I put it right here and I flipped it, it will rotate in that direction, even though the force is trying to slow it down. So it'll slow down, eventually stop, and then swing back. But what I care about is the work done by the conservative force here, by the electric force. So looking at this last formula here, I have the conservative force, therefore dot dx is equal to negative delta u. The trouble we have, I have F and X for something that's rotating. What's the work formula for rotation? What is the rotational analog of force? What's the rotational analog of position?
Radius? Or radial vector? No.
No, not radial. Angle. So when I'm dealing with rotation, this is actually torque dot d theta is equal to negative delta. We can actually take that one step further. Negative of u final minus u initial. If only we had a formula for torque for an electric dipole and an electric field. So this becomes the integral P cross E dot d theta. That's going to be equal to negative u final plus u initial. That's supposed to be a vector symbol there. Not sure what happened to it. So let's deal with this bit right here. I got a cross product doing a dot product. P cross E we've already talked about. Given our orientation right here, P is going basically pointing towards the first quadrant. E is pointing to the right in the I hat direction, which I still have defined. And so P cross E points into the board, so this is in the negative K hat direction. D theta. What is the direction of D theta?
Counterclockwise.
Okay. In terms of I hat, J hat, K hat.
Oh. Negative I hat, positive K hat, or positive J hat.
Yeah, they came up with something simpler than that. And that would get complicated real fast if they did it that way.
Is it just positive K hat?
Positive K hat. The way you would right hand rule, since I'm going in that direction, since I'm going counterclockwise, thumb points out. Almost there. So this is K hat. So my dot product will be negative. They're in opposite directions, so it's the magnitude of that times the magnitude of that, negative K hat. Sorry, negative. It's a dot product. My final answer will be not Our final answer will be a scalar. And so we end up with negative integral PE sine theta d theta. Now P and E are constants in this particular case because it's an electric dipole. They have a certain amount of charge there and there's a certain distance between them. The electric field, we're making it uniform. And so at negative integral sine theta d theta, oh, I lost my PE sine theta d theta, from some initial value to some final value of the angle. Integral sine theta d theta.
Negative cosine.
Negative cosine. So I end up with PE cosine theta from theta initial to theta final, which is PE cosine theta final minus PE sine theta, cosine theta initial. And that's equal to negative use of F minus or plus use of I. Therefore, what is a formula for the potential energy of an electric dipole in an electric field that would make this work?
Just PE cosine theta.
So if U is equal to PE cosine theta, we will be close, but not quite. If we plug in there, that would become negative PE cosine theta final plus PE cosine theta initial. Not quite what we have right there.
So negative.
Negative. What's another formula that would also work? There are an infinite number of formulas that will work. I know the hint is it's so obvious, most classes don't see it.
Or just change it to like sine theta plus 90 degrees?
No.
Oh, okay.
Oh, yeah, I guess you could do that. That's not where I was going with it. Part of this also is, for those who've had me before, giving me an some indication of the impact that some of my videos had. I can always add a constant. Because when I throw the constant in here, it's just gonna, since I'm subtracting, the constant's just gonna go away. I can always add a constant to any potential energy formula. Now, there are certain traditions when you're dealing with MGH, oftentimes they just make the grounds where H is equal to 0 for gravitational potential energy, where G is little g is relatively constant. For more universal gravitational potential energy formulas, typically you make R is equal to infinity, where potential energy is 0. Here, typically you make the vertical, so when theta is 90 degrees, this is typically where you set the potential energy equal to 0. It doesn't have to be, it's just typically done that way. So we'll squeeze in here the electric dipole, so put the ED for electric dipole. Potential energy formula is P. Well, I got PE cosine theta, that's just a dot product. It's negative P dot E. And now that you are so incredibly enthralled by this, I think it's time to take a break, calm the situation down some, come back, and talk some physics. All right, we're rolling. I think at this point I've hit all the miscellaneous topics from chapter 24, which means we shouldn't say when the quiz is going to be. I'm thinking week from today for chapter 24, flash and homework. Is this reasonable? That's it, February 1st. My memory is that we got to Gauss's law, did the pseudo derivation of Gauss's law. So we have electric flux, which is the integral of E dot dA. And then the electric flux through a closed surface would be the integral of E dot dA, with a circle in the integral sign indicating that we're doing a complete object here. The fact that it's with respect to the area means that we're dealing with some sort of closed surface. And that would be equal to the charge enclosed divided by this constant of epsilon sub naught, where epsilon sub naught 8.85 times 10 to the negative 12 coulomb squared per Newton meter squared. This is Gauss's law of electricity. And so let's exploit it. Or at least sort of look at the times in which it is convenient. If I have an infinite length of wire, or infinite length of charge, so infinite line of charge with charge density, linear charge density, lambda. Now we solved this using calculus to find the force on some test charge that I had. We're now going to find the electric field, and you can always multiply by the test charge to get the formula that we had before. We have cylindrical symmetry here, and so we're going to create a Gaussian cylinder. And again, a Gaussian surface in general, or a Gaussian shape, is one that doesn't really exist, but we are going to sort of, it's a virtual object that we will pretend is there. And so I am going to I have some cylinder of radius r. Capital R. Whichever one. The length is L. And we're going to use Gauss's law to derive the formula for the electric field at some point. I think before, I made that capital R, so this one will make lowercase r. I don't remember which. You know, we can quick flip the notes. Which one did I make which letter? It was in chapter 23, I'm pretty sure.
Big R was that, yeah, there.
Like this? Okay.
Makes sense.
We have a linear charge density, and I guess I should officially say uniform linear charge density. So it doesn't matter what length I take, it's still going to have the same ratio of charge to length. lambda is equal to charge divided by length. And so therefore the charge would be lambda times the length. So the charge that's enclosed inside my cylinder here is just going to be lambda times L. Now I know that the electric field has to be going to, assuming that the linear charge density is a positive number, I know the electric field has to be going away from the line. Because of symmetry, I know that it has to be, the direction of the electric field has to be perpendicular to the line. Because any cross components, any horizontal components, given the way I've written this would have to cancel out, because for any charge I have here creating an electric field going that way, I have one over here going, that would counter it. So any horizontal electric fields are going away, so my electric fields are all perpendicular to the line. They would be perpendicular to the round part of basically the body of the cylinder, and parallel to the end caps. Going over here. Integral is just a sum. We're adding a bunch of stuff up. Basically an infinite number of infinitesimally small things added together. In this particular case right here, I can sort of abandon the calculus to some extent and just look at what is E dot dA or E dot A at each of the three main pieces we have. Two end caps and then the body. So this, my electric flux here, would be the electric flux through what I'm going to call the body, plus the electric flux through the left cap, or left end, plus the electric flux through the right side, the right cap, I guess I've called it now. Now, since the body of this is a radius of r, of O, I want to make the radius of the cylinder be the same distance from the cylinder to the point in question. Because the electric field is the same distance away from my line of charge here, everywhere on the body of it, it's got to be the same magnitude of electric field. There's no reason why the electric field would be stronger up here than it is down here. Also, my area vector, since it's a cylinder here, area vector is perpendicular to my surface. So I have an electric field perpendicular to the surface, my area vector perpendicular to the surface, and so my dot product is just E times A. This would just be the electric field strength times the area of the body. Now the left cap. What's the direction of the area vector of the left cap here? Imagine we got a cylinder right there. What's the direction of the area vector of your left side, of the left side here? I got one finger pointing. You sort of had the right direction, but it's not a right-hand rule thing. Pardon?
Not the right-hand rule.
Not right-hand rule. What's the rule about the direction of an area vector?
It's perpendicular to the face.
Yes. And so since the face is here, it's perpendicular to it. Because it's a closed surface, it's pointing outwards. So the area vector is pointing that way. Over here, what's the direction of the area vector? And then all around the body, it's, wherever you happen to be, it's running perpendicular to it. So if my electric field is this way, perpendicular to the line, and my area vector is that way. What is the electric flux through the left surface?
Zero.
Why?
Because if it's a dot product, and they're perpendicular,
It equals 0.
you're multiplying like the cosine of 90, which is 0.
Yep. And so that goes away and that goes away for the same reason. Plus 0, plus 0. So I now have my electric field times my area of the body, I'll just put subscript B, is going to be equal to the enclosed charge divided by my constant right there. The area of the body is basically area, it's the circumference times the length. So this becomes E times 2 pi R times L. Surface area of the cylinder, of the side of the cylinder, is equal to my enclosed charge, which is just lambda times L over epsilon sub naught. And it would be bad if this didn't happen. L goes away, because L is just some arbitrary length I came up with, and so if it doesn't go away, then that would be very bizarre. And so my electric field strength is just lambda over 2 pi R epsilon sub naught. So if I put a charge Q at, I should do a different letter here. We'll make it a little q. So if I put a charge little q there at my point, a distance r away from my line, the force on Q would be Q lambda times 2 pi R epsilon sub naught in the direction of away from the line. And so however you want to express that, J hat. And that should have been the formula, although I think I could probably use different notation for the direction, but this should be